Morning. Hope you had a good break. Um, yeah, I'm sure when it comes to questions, first, might have to remind you that you're in this course. I don't know, for me, a week is just a long time. I tried just getting, when I sat down to plan the lessons and everything, I did it right away because I knew after a week, it's like, whoa. So last time we did lesson 2.6, higher order derivatives. That quiz, I believe, that some of you just got, I think I handed back before the break, but some of you weren't here, so. So let's begin with 2.6 questions. Yes. Okay, 37 on 2.6. Okay, I'll find my way here. 37. Find the second derivative and solve the equation f double prime of x equals 0. Okay. So what we are given is we have x times the square root of x squared minus 1, which we probably could think of as what? X times x squared minus 1 to the 1/2. And so since there is no neat square root of x squared minus 1, you probably have to differentiate this by using the product rule. So f prime of x, the first times the derivative of the second plus the second times the derivative of the first. So see if that makes sense first of all. The first times the derivative of the second, and that meant what? Power rule and chain rule, and then plus the second times the derivative of the first. Well, that part turned out to be nice and easy. We should probably try simplifying this. Let's see what we can do. Well, the 2's cancel in this first term, and we have an x times an x, so that'd be an x squared. And then this is what in the bottom? Well, I'm not going to go back algebraically. Why not? Because aren't we going to have to find another derivative in a second here? So I shouldn't do that, but let's just write what? Okay, and then so let me just see. Do we have this right here? So there's the first derivative. So should we go on and do the second derivative? Anybody have any, do you or does anyone else have a question on how I arrived at that? Okay. So I'm going to do the product rule again on this guy. The first times the derivative of the second plus the second I'm going to start running out of space here, times the derivative of the first And I still have this to differentiate. So I'm just going to continue below it here. Now I have to differentiate this. I could just use the power rule. Okay, now because I next need to set this equal to 0, I really need to, now I need to algebraically get this into some kind of sense of some better form here. So let's start working on this term here. Once again, the 2 and the 2 over here will cancel. And now I'm going to have an x squared times an x. That's an x cubed. I've got a negative, so I better get a negative out there. And then I have this thing on the bottom, which is what? The square root of x squared minus 1 cubed. Sorry for how sloppy that is. That takes care of that guy, and then the second guy over here is just, sorry, I'm over here now. This guy is a square root on the bottom. And we have a 2x on the top. And then lastly, in term 3, the 2's cancel again, and I have an x over the square root of x squared minus 1. You know, to make our job a little easier, I think I'm going to get a, because remember, our whole goal is to take this second derivative and set it equal to 0. And what did it say? Solve? I can't even remember. 37? Yeah, solve it. So I'm going to go further here. Okay? Let's get a common denominator. Would it make sense to all of you that if I multiply by the square root of x squared minus 1 squared, that'll give me my common denominator here. If I multiply this by the top and bottom of these two fractions, wouldn't that give me a common denominator that would agree with this? Because here I have x squared minus 1 3 times under the root sign. Here I only have x squared minus 1 1 time under the root sign. So don't I need to add 2 more, so to speak? So I want to take this and multiply it by the top and bottom of this and the top and bottom of this, so that I'll have a common denominator. Can everybody see that? It'll get real messy to show, so I'm just going to apply that, okay? So I want this to be multiplied top and bottom here and here. After I've done that, the good news is I'll have one big happy denominator. Of course, this term doesn't change, but what's going to change over here? Well, I'm going to have 2x times this. By the way, what's another name for this? What's the square root of a square? Don't the square root and the square undo each other? So won't I just have x squared minus 1? So that'll be 2x times x squared minus 1 plus x times x squared minus 1. Okay. Now remember, we're setting this whole thing equal to 0, right? So I have good news for you. Can't I just take both sides of that equation and multiply it by that denominator? And then it'll be goodbye denominator, because on the left it'll be 0, on the right it'll... So now, can everybody see that my next line would be And you know, let's multiply out this numerator. My next line would look like this. Plus 2x cubed minus 2x plus x cubed minus x. Combining, what do we get? Oh, wait a minute, that's not right. There's going to be what? Negative one of them, two of them is plus 1, but I got another one over here. So I have 2x cubed, and then I have what? Negative 3x. Does that look right? And then, now it's pretty simple, isn't it? Can't I just factor an x out of that? And then set each factor equal to 0. And then we can just, this one we already know, nothing to solve there. Here, and x equals what? Plus or minus? Square root of 3/2. I don't know, did that all pretty fast, but according to this, I have 3 times when the second derivative will be 0. One of them is right over here. Don't forget about this guy at x equals 0. And then x equals plus the square root of 1.5, and x equals minus the square root of 1.5. What? Just a reminder, what does that mean when the second derivative is 0? By the way, is that dumb or what? I didn't think about that term the entire vacation, but now when I wanted to bring it up, now I know it. You remember I couldn't come up with it last time at all? It's the point of inflection. You remember that? It goes, you don't remember? Okay. Well, I would say about 3 times I said, oh, what is that called? What is that called? Well, anyway, it's called the point of inflection. And it just popped in there. Weird stuff. I guess being off the booze helps. Yep. What happened? Yeah, I said it, but I didn't show it. Okay, when we have this equation, I simply multiply both sides of this equation by the denominator. So on the right, that means it canceled. And on the left, of course, anything times 0 is 0. So it looks like the denominator vanished. Actually, it did. But that's the reason. So anyway, it means that this particular graph has 3 points of inflection. 0, plus square root of 1.5, and minus square root of 1.5. Okay, so there's number 37. That one got to be fairly involved because the derivatives got a little bit messy, and then we had this kind of an ugly algebraic form we had to deal with. Other questions? John? Sure. Number 9. Find the second derivative. Okay. Our function is three times the quantity 2 minus x squared cubed. So we could leave this like it is and think of it as two things being multiplied and do the product rule. Or we could cube that 2 minus x squared thing, multiply it all the way through by 2, and then we would just have a polynomial, and then we could go ahead and crank away. I almost think in this case, because I have to do 2 derivatives, maybe this time I'm going to go ahead and just cube that thing in parentheses. But, you know, they're both ways are valid. Well, okay, so off sidebar. What's 2 minus x squared cubed? Well, 2 minus x squared squared would be first term squared. The product of the two is minus 2x squared, doubled. And then the last term squared. And then we'd have to do it one more time to get it cubed. 4 times 2 is 8. 4 minus 4x squared minus 8x squared plus 4x to the fourth plus 2x to the fourth minus x to the sixth. Bringing that together, I get negative x to the sixth. How many x to the fourth? 6 of them. And then squareds, I have what? Minus 12 of them. And then there's plus 8. Does that look right? So now I'm going to rewrite this, only I'm going to take this guy, this is the part that's cubed, and I'm going to multiply it by 3. And then I get negative 3x to the sixth plus 18x to the fourth minus 36x squared plus 24. Okay, so finally I've got another name for f of x. Now f prime of x and then f double, we're supposed to do double, right? Yeah, f double. And I think that's as far, yeah. There, I should separate these because this is all me finding the cube over here, but looks like we've got the second derivative. So I don't know which is better in this case, John. I suppose if I was really pure, I probably should have used the product rule to practice that, but we should have come up with the same result. So you always have this decision to make, don't you? Which way shall I go at it? Shall I use the product rule, or shall I hammer out that thing to a power and then just use the polynomial rule? So should we do maybe one more, if you'd like, kind of bring things back? 29. We're supposed to find the what? The third derivative, and they gave us the second. So at least we only have one to go, huh? So they've given us f double prime of x. And the answer, or the double prime of x is 2x minus 2 over x. You know what I, again, two approaches. Approach one, leave it like it is and use the quotient rule. Approach two, simplify that thing a little bit algebraically, and I think it's going to be a little easier to differentiate. I'll take approach two. If we divide that, isn't that the same as dividing each term by x? So wouldn't that look like this then? And then isn't that the same as? And now, let's just go one derivative further. Well, that's nothing. And maybe this one I'll do the other way too. Let's just do the quotient rule this time. Okay, quotient rule. Denominator times derivative of numerator minus numerator times derivative of denominator over denominator squared. All of a sudden my mind went completely blank, because then minus 2x plus 2. And you can see we got the same result. 2 over x squared. So there we did a combination. We did them both. We did it both ways. You know, it wouldn't hurt periodically take a little time and do things both ways as a checking device. I know you may not have that luxury on a test, but not a bad way to prepare for a test. Yeah, and it's, you know, that reminds me, I should talk about the calendar. I've planned out things to, to Easter break, which isn't very far away, is it? So anyway, today we've got this, I'm supposed to go through lesson 2.7 today. Shouldn't be too big of a problem. Then Wednesday and Thursday, I'm planning 2 days on lesson 2.8. It's just a harder lesson, takes a little longer. It's called related rates. So that brings us to Friday. And Friday I've got down questions on that related rates and begin review. Monday, second day of review. Wednesday, test chapter 2. So we're shooting for a little over a week from now having our second chapter test. Okay? So that's the overall plan of attack. All right. Well, let's get started on implicit differentiation. What we've been doing up until now is called explicit differentiation, even though I haven't told you that. Implicit, you know, means kind of a, I don't know, implied. The word implicit relates to the word implied. You see, here's the problem. Up until now, all the functions we've looked at have always been y equals something. And on this, when I say something, it's always what? Something in terms of x, right? Or t, or one single variable. So far, that's all we've had. But what if you can't solve for one variable real easily? You know, like, I'm trying to think of a good example here. Is there a way to solve this for y? See, I could get the y's together. I could do this. You know, I could say y minus xy equals x squared. And then I could, I suppose, factor a what? A y out of the left? But the problem is, I guess this one works. That example. Because I could then say, okay, but there are some that cannot be solved for y, and I went blank here. So yeah, let's just take, yeah, I know what all I needed was, no, that doesn't do it either. I'm trying to find a good one in the book here. Well, let's just leave it at this. There are some equations that you can't solve for y very well. What if, yeah, what if I'd have had this, for example? Now you got a real stinker of a problem. Anyway, the lesson today says it's okay. Even if you can't solve for y, you can still find a derivative. And it's using this technique called implicit differentiation. And I'm going to, I guess, yeah, we'll just go into example from the book here. I'm just not finding the ones I expected to find here. You guys all know the chain rule. I could never teach you this lesson if you didn't know the chain rule. So let's just go to a new page. Okay, let's take the example on top of page 150. They call it example 4. Y cubed plus y squared minus 5y minus x squared equals -4. Okay, you're just not going to solve this thing for y. Okay, so here's what we do. We're going to differentiate this whole thing right where it is. But I want to, now up until now, I've mostly been using this notation. Instead of y, we've been using this. And in place of a derivative, we've been using, usually we've been saying that. But another way to say derivative is the derivative of y with respect to x. Sometimes that notation comes in handy. So in effect, what I'm going to do is take this whole thing and now what, by the way, that's Leibniz notation. Gottfried Leibniz, Germany, and Isaac Newton, Great Britain, simultaneously discovered calculus. And although there have been arguments about who actually did it first, actually Leibniz was first, but he didn't publish his results. Okay, here's where the argument comes in. Leibniz really, we know from looking at some of his diaries that he actually knew it, but he didn't publish it. I don't know if he was afraid or what. Isaac Newton comes along and rediscovers it on his own without having seen what Leibniz did. And everybody goes, wow, this is cool. And then Leibniz says, I knew that. You know, you've all heard people not real nuts about people who do that, you know. But anyway, he kind of said, I did that. And Newton said, well, how come you didn't tell anybody then? You know, you can almost see them talking to each other. Well, I made mine public. What are you hiding? You can just hear the arguments ensuing. But anyway, basically they've both been kind of tied, given credit for this. But Leibniz notation is that dy dx. Leibniz notation has some advantages to it. In fact, Newton's we don't even make public. Newton used something called fluxions. That was his way of saying derivative. And his notation wasn't so hot. The cool thing about this dy dx is it says, I want you to find the derivative of y with respect to x. Up until now, that hasn't been an issue because we've only had one variable. Or remember, you've seen some t equations. Find the derivative of y with respect to t, right? The time equations, the ones that relate to physics. Okay, so remember, we're differentiating with respect to x. Anybody else is kind of an outsider, and we have to do the chain rule on anyone else. Guess who the anyone else is in this problem? Y is the outsider. We want to differentiate with respect to x. So here's the deal. Whenever you deal with an outsider, a foreigner, you got to use the chain rule. So it's kind of like y is some function of its own, okay? And you know, whenever you have an inner function, what do you have to do? You have to multiply by the derivative of the inner function. So here we go. Differentiate y cubed. Well, first of all, the regular power rule says, wouldn't that be 3y squared? But because y is an outsider, I got to use the chain rule too. I got to differentiate that. Now I could write that as y prime, but right now I'm going to write it this way. Okay, now y squared. Well, that's, first of all, the power rules, no problem, but that's an outsider. So I have to use the chain rule. Next term. Well, that's minus 5. But y is an outsider. Now comes an x. No problem. Negative 2x. And what's the derivative of a constant? Okay, so now I've got this weird-looking statement here that has some more derivatives in it. The whole idea is we wanted to find dy dx, right? So now let's do a little algebra to find dy dx. You notice it's in 3 terms. Shouldn't we, like, first of all, get the only thing that doesn't have a dy dx on it off to the right? So I'm going to add 2x to both sides. And then what happens when you factor out a dy dx? Wouldn't that look like that? And then, can you solve for dy dx? Sure, all we got to do is divide both sides by this big multiplied quantity. So dy dx equals 2x Now, I know that looks strange. It's the first time we've seen a derivative that has both x's and y's in it. There she is. We actually found an implicit derivative. So now the key to this whole thing is that whatever you're differentiating with respect to, and 99% of the time that's going to be with respect to x, dy dx. Whatever you're differentiating with respect to, if you have any other variables there that are non-x, you've got to use the chain rule. And that's what we did right here, and right here, and right here. And here we didn't, because that was what we're differentiating with respect to. Okay, well then, when you're all done with that step, just isolate the dy dx, solve, and you've got your derivative. So, implicit derivatives actually will have more than one variable in them. Now, for example, what if we asked you, oh boy, I don't know, they don't have this down for this problem, but I guess they do. They have a couple points in the book. If you look in the book, by the way, you can see the derivative in the book too. And that's cool. I did it the same way they did, so you can see the same process there. They give us 3 points. One of them is 1, negative 3. So here's one of the points on that original, I won't call it a function, but on that original equation. Can you find the equation of the tangent line to this graph at this point? Well, we know the derivative, don't we? So I'll just put it this way, what's dy dx, and I don't know what the right notation is here, what's dy dx at the point 1, negative 3? So now we just take this equation, and we got to plug in not only x, but y, right? Because we have y's in there. So plug in a 1 for x and a negative 3 for y, and what do you get? 2 on the top, 27, minus 6, minus 5. So I come up with a derivative at that point of 1/8. So it's no big deal. You just have to plug in both x and y now. And then you can, from there, you know what to do. You would set up a mx plus b form, where m is 1/8. And then, when you plug in your point, it's way up on top there, but I have to plug in that point 1, negative 3. And what do we have to do? Subtract 1/8, so minus 3 and 1/8, or negative 25/8. So equation so, I mean, most of this is old stuff. This is good news. Implicit differentiation is comes in very handy because you can't always solve for y. I'm going to go right to the assignment now and take a few. Yeah, it's 12. Here's some examples. I should have looked on the assignment. Okay, here's a good example. Maybe not. I got to think about that. Yeah. I guess let's do number 10. Sorry. xy minus y squared. On the bottom, y minus x. Okay. Find dy dx. And dy dx is what you've been finding for quite a few lessons now. Just that we haven't used that notation. I maybe should have more. Well, can't we multiply both sides by y minus x, giving us okay. And now let's differentiate. We're not going to try to solve this for y. The problem is this mixed term right here. So here we go. Dy dx of that whole thing is. All right, start with this term. Two things being multiplied, don't I have to use the product rule? So the first times the derivative of the second. Well, with the derivative of y, it's like y to the first is 1. But then, because it's a foreigner, I have to multiply by, use the chain rule, plus the second times the derivative of the first. So here's the product rule. The first times the derivative of the second plus the second times the derivative of the first. Okay. Now, how do you take the derivative of minus y squared? Well, first, just use the power rule. And now, because y is a foreigner again, I got to use the chain rule. Right side, 1 times dy dx minus, and the derivative of negative x is minus 1. Okay, so now all I really got to do is get all my dy dx's together, solve for dy dx. All right. I guess I didn't need all those ones in there, but so I will just copy this one. And I'm going to put this one next to it. And now I'm going to subtract this one. So I'm just getting all the dy dx's on one side. And now let's leave that one there, and let's get that one over there. And that's what, minus y? All right. Now let's factor a dy dx out of the left. And then to finish it off, we want dy dx by itself. So take that big old thing that's being multiplied and divide both sides by it. Again, implicit differentiation. So the biggest thing you're going to have to get used to is this, this chain rule being used. Well, we've never differentiated y's before. So today is our first crack at it. Good news. Y gets differentiated just like x, with one very important exception. Every time you do something in y, you've got to use the chain rule and always multiply by dy dx. Then the rest of it's not too bad. You wind up using algebra to finish it up. Yes?
For the first part, x, y is y is x, not a 4. Just because it's with y.
Simply because they asked you to find dy dx. Whatever is on the bottom of that, find dy over, this here, it's because of this right here. And if you look in the directions, I know you haven't probably seen that, but the directions say find this. Whatever is down here is not your foreigner. And so basically that's the rule. So it's because of what you're differentiating with respect to. If I said find dx dy, then x would have been the foreigner. They're not going to do that, by the way.
For the first term, it's xy. Yeah, x minus y squared.
Right.
So,
oh, in that term, okay. So I've got the first times the derivative of the second plus the second times the derivative of the first.
okay. All right.
Product. Who else had their hand?
3 steps up to the bottom. Yep. And then, so negative y and then what is that component?
You just took this one y and subtracted it from both sides. Anybody else? Let's do one more with the remaining time here. Well, at least we can get started on this. How about if we do uh, 22? Number 22 says square root of xy, and that's equal to x minus 2y. The directions are find dy dx. So, and by the way, that's basically, that's what they're always going to ask you to, I mean, unless it's a problem with t in it, then they might have you do it with respect to t. But you're never going to be doing dx dy. It's dy dx. So, good news, I don't have to do any pre-algebra for this. I can just say, all right, let's find the derivative of this whole thing. Well, I might want to rewrite it like this. There's one thing I might want to do. I might want to write this as xy to the 1/2 power. then otherwise I'm not going to do anything new. Okay, so here we go. Well, first of all, I got to do a chain rule here because I have an outer and an inner function, right? So what's the outer function? Well, use the power rule, 1/2 times what's in parentheses to the minus 1/2. But now I got to do the chain rule because I have an inner function. Oh my, and in the inner function I have a product rule. Okay, so here we go. Times the first times the derivative of the second plus the second times the derivative of the first. Well, that's a 1. Okay, right side, derivative of x, that's easy. The derivative of minus 2y is minus 2. But because I'm dealing with y, I have to use the chain rule. All right, now all we got to do is get our dy dx's together and do a little bit of algebra, and we got it. So let's simplify. You know, and they don't like fractional exponents. So shouldn't we write this as and then what? We got an x. So I could have put an x there. And then that's times dy dx. Should we then add this minus 2 dy dx to the left side? And then let's just subtract y. So all I was trying to do, I'm sorry, I did a couple things there. I rewrote the thing to the fractional power, and I'm just doing the gathering of the dy dx terms on the left. Next, we can factor out the dy dx terms. Sorry, no equal. Times and then, even though it's not complete algebraically, we can divide both sides. And we probably want to keep simplifying that some more, but and by the way, that's supposed to read xy right here. Okay, so bottom line, you don't even have to solve for y to differentiate. We call this implicit differentiation. What are you differentiating with respect to? I believe the book will always come right out and say, find dy dx. Find the derivative of y with respect to x. Then every time you encounter a non-x, you have to use the chain rule. So, I don't remember what the assignment is, so I got to look. Did anybody look? Probably not. I'm going to change it. It says 1 to 45 odds. Let's do every other odd. So do 1, skip 3, do 5, like we did the other day. Got it? 1, 5, 9, ... 45. Excuse me. Have a good one.